Should be 3.3. No, this is should pointing to 3.2. This is weird. This makes no sense to me. What are you saying, bro? Hold on. Dog, come on, dog. What the fuck? Hold on, something's wrong. It's 3.3 for sure, which is fine. Sure, whatever, dog. Annoying. Testing 1 to 3, 1 to 3. Okay. Very annoying because last 1.5 or 2 hours of study was just not captured because the streaming software started bugging out, I guess. That's just so annoying, dude. I was just like studying so hard, but the streaming software decided it will not work, which is fucking annoying. Anyways, I was studying the examples. Let's see. Anyways, I was just studying the examples here. Okay, prove that with probability minus, at least probability minus 1 minus 1 by n. The process of drawing things takes n log n steps. Okay. Okay. So let's see. There's a hint that particular coupon is never drawn after n log n steps. Sure. Okay. Sure. Okay, so assume that the probability okay, so I'm assuming that to draw a coupon, the probability that the coupon will be drawn is 1 by n, right? The probability that a coupon will not be drawn is 1 minus 1 by n. So the probability that a coupon will not be drawn is 1 minus 1 by n. So if you're using Markov's inequality, then we got to like figure out that okay, so if you're using Markov's inequality, then anyways, what was I saying? Okay, if you're using Markov's inequality, then we are saying the probability that our algorithm won't succeed after some expected amount of time is something, right? We have to prove that. Now I'm saying that the probability that the algorithm actually runs, okay, the probability that the coupon is not drawn, ith coupon is not drawn, some coupon is not drawn, is 1 minus 1 by n, because probability that it is drawn is 1 by n. So probability that it is not drawn is 1 minus 1 by n. If I repeat this t times, then it's just 1 minus 1 by n to the party, right? Now I'm saying that my time steps are some c n log n, right? C n log n. So 1 minus 1 by n, c n log n. This is the amount of time. I don't know. Let me just figure this out. Okay. I remembered how to do this. I forgot, I guess. Okay, hold on. Let's see. When we say the process takes n log n steps, we say that it takes c n log n steps for some constant c. Sure. Coupon not being drawn after c n log n is sure 1 minus 1 by n. Okay, this is perfect. Honestly, this is perfect. Oh, there's a standard inequality that we need to use. Ah, okay. Uh, some useful standard inequalities to keep in mind are these: that 1 minus 1 by n to the power n is less than equal to e to the power minus 1, or um, 1 minus 1 by n cn log n is less than e to the power minus c log n equals n to the power minus c equals 1 by n to the power c. And okay, union bound step is basically just saying that you do n times 1 by n to the power c equals 1 by n to the power c minus 1. Sure. So the probability of success, okay, so prob of success is at least 1 minus 1 by n to the power c minus 1. If c equals 2, it c yields 1 minus 1 by n. Basically, that's what it says. So we have to prove this probability figure, and we have to say, okay, so we know the process takes n log n steps. So if we take n log n steps, we always have to remember that it just translates to c n log n. And if you just remember this identity, everything will revolve around this identity. The c n log n could change maybe, right? And this could become something else, but should be straightforward, I believe. Anyways, let's go to the next PDF. Let's make a log of this. We did 1:41 p.m. Finished going through example 2. Okay, finished going through problem sets. Let's see, 25 and 26, right? Set question 25 and 26. Okay, let's go through this now real quick. Okay, so LPs. What is the topic name here? Real quick, let's see. Let's check this shit out. Okay, randomize LP rounding. Okay, so oh my god, sorry dog. Randomized LP roundings. Let's see. Let's think. Randomized LP roundings is just okay. Okay. While LPs often captures a problem exactly, equality is allowed, strict inequalities are not allowed. LP solvable in polynomial time. Sure. Okay. Randomized LP rounding. There's a theorem that says LPs solvable in polynomial time. Okay. Captures the problem exactly. Design approximate algorithm. So we can do 2 minus approx or some approx. For a max problem, algorithm will be greater than half a optimal value. Sure. For min problem, algorithm will be okay. Sure. Cool. For a max problem, we know alg is greater than equal to half optimal value. For min PBLM, alg is less than equal to 2 times opt value. This is one important thing. Now, idea is to approximately solve a discrete problem using LP. Solve an LP relaxation. So, okay, you relax an LP, rounding, convert the optimal fraction null LP solution to integral solution. Okay, maybe losing something in objective. Sure. Okay, so set cover, for example, is one problem. NLP based log and approximation. Define Fourier reset. Minimize this. I remember this from one of the assignment examples. It's pretty straightforward. And this is also pretty straightforward, honestly. So relaxation. Claim 1. LP value less than equal to optimal set color. To prove this, first to show that feasible LP solution of a value. Consider optimal solution. Okay. This LP feasible X. Okay. Optimal set cover. Okay. Claim rounding 2. There's a randomized rounding algorithm that has expected cost LP value times log n times optimal set cover, okay, which is less than log n times. Okay, for set cover you do this. Claim with probability 1 by n minus c plus c minus 1. Solution feasible after step 2. Okay, consider any element E that belongs to n. So these proofs we don't need to use, but we just need to use like its result. The probability that E is not covered is just the sum, the product of these things, and it's less that this shit. Okay, algorithm is feasible after step 2 with probability 1 minus 1 by n. Oh, this is exactly what was expected in algorithm example 2, I guess. This could be asked essentially, right? I don't know what to grab from this or what to pick from this, honestly. Let's see. Thinking. The notes aren't very clean, honestly, but let's see. Anyways, entire syllabus, sure. 330 to 445, line algorithm plus randomization. And what is this one? Concentration inequality. What is this? Number of heads, 1 0. Want to understand SN greater than. Okay. Control the moments of random variable. Okay. First moment, Markov's inequality that we had seen before. Okay. Second moment, Chebyshev inequality. Okay. Higher order moment. Chernoff holding. I don't know what this means. Example load balancing, sure. Hmm. I could take a calculated risk and be like, okay, that this ain't coming. Because this is a bit too crazy, not gonna lie, dog. Actually, let me see the last question. I haven't ever solved this one. Okay. In a max two-sat problem, there are n Boolean variables 1 to xn. We define a literal to mean a Boolean variable or its negation. We are given m clauses j1 union j2 of two types depending on the number of literals in them. Each clause is j1. Okay, hold on. So, sure. Since the max, okay. This is a two sat problem. Okay, we are given an where m clauses j1 of two types or two types depending on the number of systems. Each clause in j1 consists of a single literal u, and a clause in j1 is or of two literals v u v y and z, or some literal y and z. The goal is to find the assignment of variables. Okay. Okay. Since this is a maximization problem, is NP hard, we will design LPX approximation. Consider the following LP relaxation. We have variable zj for jth clause. Okay, hold on. So what is discussing LP relaxation, right? This part's discussing LP relaxation, right? Wait, which is this? No, this is the online algorithm. So what I could do is I could just scour for facts from this one, and I could just write down facts, right? Okay, so let's just do set cover maybe. So the strategy has been changed now. Okay, like update to the strategy. Let's do an update to the strategy. Updated strategy. Quickly go through all PDFs and get all facts and theorems in your sheet. Next, abandon all PDFs and just go through problem set 8's last two questions again to understand the pattern of question that could be asked. Okay, so I'm just thinking that this could be like some kind of easy thing. I know that the professors will never, you know. Okay, gonna grab myself another bag of chips because I'm just fucking hungry all the time. Okay, I'm back with my chips. Okay. Wow. Okay. Cool. Okay. Belongs to the universe. Find the minimum number of subsets such that their union is some n. Okay. So it's NP hard to get a log n 1 minus epsilon approximation theorem and LP based big O log n approximation. Okay. 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 Claim 2 is around rounding. There is a rand round alg that has cost which is less than equal to okay. I don't care about the proofs. Okay. 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 Fair. Just have the set cover example, right? The main idea here was this. Yeah. Nice. Okay. Okay. IMP thing would be probability that there exists an edge which is not covered is equal to the probability that all elements E is covered. This is less than the sum of and which is less than equal to n times 1 by nc which implies alg is feasible with probability greater than or equal to 1 minus 1 by n. Okay, we gotta figure out this mapping honestly, but let's just say that why am I writing PM, dog? Actually, you know what, dog? You know what, dog? I'm gonna keep working on this, but I'm gonna close my stream because. Ah.